Yeah, thank you. Thank you so much for the invitation. Hi, everyone. As mentioned, I am Saurabh and I work in generative AI field. How many of you have used any generative AI tools before? How many of you want to learn more about it? Interested in it? Okay, yeah. So we'll talk about large language models today, and I have made this talk in such a way that it is understandable by everybody. So you do not need to have any background in how these AI systems work, and I'll try to explain how these work and what are their applications. It is going to be an interactive lecture, so feel free to stop me and ask any questions. That way it would be more interactive. Okay, so generative AI. Generative AI means that you can generate things which don't exist before. So there are two tracks of generative AI. One is image and one is text. So in scientific languages, it's called vision models and language models. So here on a vision model, if you ask it to make any image, it can make it. So I just said MMA fighter eating noodles on Mars, cartoon style, and it came up with this image. And you can see that there is an MMA fighter sitting on Mars eating noodles. It's a very weird thing to imagine, right? This image doesn't exist anywhere in the world. No artist made it. But still, with just one text prompt, the AI could make it. That means these systems understand what an MMA fighter looks like, what noodles look like, and what Mars looks like. And they actually combined it together and made an image. And that's why these systems are very powerful, that they can imagine things and make things which do not exist. Second category is language models. So I asked a language model, write an 8-line poem about chemical engineering. The poem should rhyme at every line. And it came up with this, right? There is no image poem like this, but it wrote it very, very quickly. And looks like chemical engineering, right? It rhymes. In reactor tall, where chemicals combine, a delicate dance of molecule in line. So it rhymes also. It makes sense also. It didn't exist. So how these systems actually are able to come up with things, very weird things which you ask them to do, and sometimes they are very useful also. So why do we care, right? It does creative things. It's okay. It's good for fun. But what are the applications? Why they are important and why everybody is talking about it? Reason is they are very important in a lot of fields. For example, in healthcare, you can get personalized health advice from these large language models. So there is a company called Hippocratic AI which is making virtual nurse, and you could imagine that the healthcare system is very, very busy and you don't get access to healthcare the moment you need it. But if you have a virtual assistant who you can call or who you can talk to when a nurse is not available or a doctor is not available, who can help you out, it would be very powerful. It can help in diagnosis. If you have multiple reports, you can feed in these reports to the LLM and then ask the advice and what it thinks, and it could be very helpful in that. Reporting, there are a lot of reports which are generated in healthcare industry. It can make reports, summarize reports, so it can actually reduce a lot of effort on healthcare workers. It can have a huge impact. Education, it can be a personalized tutor. So it can actually tutor you based on your capability, based on who you are, and it can tutor you in various languages, in various subjects. Automated grading, there is a lot of effort gone into grading, as Professor would realize. It could help in these efforts, language learning. So the LLMs can translate text from one language to another with very high accuracy. So it can be helpful in teaching language. In software engineering, there are a lot of softwares which actually can write softwares by themselves. You just give them a command, tell them what software you want to be written, and then it can write the code. You can debug a large piece of software. So you can actually feed in the software and you can ask what is the bugs in the software, and it can tell you where the bugs are. In businesses, you must have used some of these. There are a lot of chat bots now businesses have integrated. So you are actually talking to an AI system instead of talking to a person, which understands the business products, business processes and can answer you very accurately. So it actually automates the businesses, lower their costs, and it's very helpful. Personalized marketing in different geographies, you can actually prepare marketing materials and do marketing according to the geography and the people you're targeting. Content creation, you might have seen a lot of hype on AI influencers making different YouTube videos with AI, making a lot of Facebook posts with AI, LinkedIn posts. So these things can be done with AI. And in the field of cybersecurity, AI can actually help in identifying and thwarting cybersecurity threats. So this slide is a snippet that these large language models are really helpful in various industries, and that's why it is going to be more and more important in the future. Okay, so when we are talking about large language models, let's understand what language modeling is. So language modeling is basically teaching a computer a language. So we are speaking in English. How does a computer understand how English is written, spoken, and understood? And that's what these large language models are doing. And the technical term of this field is natural language processing, which is NLP. So how do we do that? We actually transform the language in numbers, because computers do not understand anything except numbers. And then we basically make large models for it to make sense. And then once you actually train the model, make the computer understand the language, you can perform these tasks such as autocomplete, translation, or question answering. So what is a large language model? For example, if you have used a ChatGPT model ever, it's basically a large language model which is sitting behind the chat interface you're using. So whatever question you are feeding in, it is going to the model, and the model is going to give you the answer. So very fundamentally, it's a bunch of mathematical equations, very large number of mathematical equations, which are fitted together, which process what you are feeding in, and then it outputs. It's basically like an equation you solve. And the fundamental unit of these models, which are also called neural networks, is a neuron. And it looks like this. It's a neuron. It's a mathematical equation. If you have two inputs, x1 and x2, and these are numbers. The output of a neuron is w1 x1 plus w2 x2 plus b. And these w1 and w2 are weights. They are parameters of the equation. They are called weights. And b is also a weight. x1 and x2 are the inputs. So think about the numbers which come from your text. They are actually computed in this unit operation as w1 x1 plus w2 x2 plus b. This is also called a perceptron or a neuron. And this is a fundamental unit. And imagine this unit is replicated millions and billions of time. So you would understand that the w1, w2, and b parameters are also replicated billions of times. So in a large language model, you have billions of these w and b parameters and other parameters, which you actually use to perform that mathematical calculation and give the output. So these are very incredibly large and complex, and they are designed specifically to understand and respond in a natural language. However, they are basically at the heart of it mathematical operations. They are self-contained. They do not need to access the internet for making their calculation. I can host some of these models on my laptop, switch off my internet, and still it will give me the answer what I need. Now I'll just focus on the landscape of these large language models. There are many available, and as you might be hearing, there is a huge advancement in the research of these models. Every week there are new models coming in which are better than the previous. Some of the best models available are ChatGPT from OpenAI. So their best model is GPT-4, which is actually the best model out there so far on various benchmarks. But there are two types of models. One is closed source and another is open source. Closed source model is where you do not know the model architecture, you do not know the weights. The company owns it and they do not share it with public. So you can ask the questions to these models, for example, use the ChatGPT, but you can't really know what is going on in the background. So OpenAI's ChatGPT, Google's Gemini, Anthropic's Cloud. These are some of the most popular models out there. In the parallel universe, there are some open source models where some companies and some organizations have kindly open sourced their model architecture and the weights. So for example, Meta's, which is Facebook, Llama series of models. So Llama 3 was just released like 2 weeks ago. And this is the best model which is open source. So they have open sourced the entire model architecture, all the weights for the community to use. So you can actually download this model in your laptop and run this model in your laptop. You can actually, if you are more interested in building on the top of this model, so you can actually use this to change the model to teach it whatever you want. There are other models which are available, and there is one model just Microsoft recently released 5.3, which is also very powerful, which is small model. So, and then now let's talk about the sizes of these large language models. So whenever a company or an organization releases a model, typically they release at least two models. One is smaller model, which is around 7 billion parameter model, and one is bigger model, which is around 70 billion parameter model. So when we talked about the neuron architecture, it had three parameters, W1, W2, and B. Right? You can think about how big and complex these models will be if they have 70 billion parameter. So 70 billion parameter, each parameter is 2 bytes. So it's basically for downloading this model, downloading this model and hosting on your computer, you need 140 gigabytes of space. So this is that large, and this needs like around 14 gigabytes of space just to store it. And these are very, very big and powerful models. And then there are some companies which are working on small language models, which are smaller models which can be used, which is 3.8 billion parameter, which is basically Microsoft's 5.3, which they just released. Why people do these gradations? The 70 billion parameter models, because they are large, more complex, they can perform tasks in much more accurate. They can perform much complex tasks. For example, you can actually ask the 70 billion parameter model to write the entire piece of software or write entire website, let's say. You can give some parameters. You want to make a website of me. These are my qualifications. Just make this website. It will give you the entire code. But these take large resources, large memory. They are slow to run because these are mathematical operations you are doing. If you are doing large number of operations, it takes a long time to run these models. So if you are actually using these models in your company or in one piece of software, you might want to use it smaller models. So just think about if you ask some question to an LLM, if it is taking like 1 minute to get you the answer, you will be frustrated, right? That's why companies sometimes need these smaller models so that they can run these models much faster and get the answer to the customers much faster. Now, how these models are made. So there are two things happening in this model. One is training, one is inference. Training is the process of building this model. For example, when OpenAI was building ChatGPT before they released it, they actually were doing the training of the model. But once they released it, when users can use it, that is called an inference. Inference is just you have a trained model, you have known weights, but you want to run the model. So you give an input, so you ask a question, and that input is run through these model and you get an answer. That is called inference. So inference is much cheaper to do than training. And training is incredibly complex and incredibly time consuming and money consuming process. You and I cannot do this training process. It needs thousands of GPUs to be run for several days to train a model. Okay, so let's talk about how these models are trained. So first is architecture selection. So architecture means you need to select what kinds of these mathematical equations are being fitted in the model, how big it is going to be. So you select the size. Is it going to be 3 billion, 7 billion, 70 billion? And there are a lot of mathematical equations. The neuron I showed you that was a multiplication and addition operations. It's basically a linear combination. But you can see here, this is one of the unit, which is called transformer, which goes into these large language models. You can see a lot of operations are performed. Each block is a complex mathematical equation, and you see a lot of operations. Each arrow is when a mathematical operation is talking to each other, and you can see a lot of operations are happening. So first you actually select the architecture of your large language model, and then you actually train it on a large amount of data. So typically these 70 billion models are trained on entire internet. So entire internet means all the web pages, all the Wikipedia pages, a lot of books, a lot of content in different languages. Some of these models have also been trained on social media posts like Instagram, Facebook, etc. So what is training? Training is basically learning those weights. So when a model is being trained, you are trying to learn those weights, what these weights are, and how these weights can be used to optimally perform the task. For example, question answering. So once you learn the weights, your model is fixed and you can use it for performing these tasks. So let's take an example of Llama 3, which was just released by Meta, trained on 15 trillion tokens. So I'll come to what tokens are. Tokens are basically a subset of words, and these computer models use tokens because that is more powerful in training these models. It was trained on 30 languages, so 95% of the tokens were in English, but the rest of the 5% was in different 30 languages. Their biggest GPU cluster were 24,000 GPUs. So for example, if you, some of you own like a PS5 or Xbox, that's one GPU. So imagine having like 24,000 of these things and using it simultaneously. So you and I cannot do that. It needs a large organization like Meta or Google to do this. So they basically, for one model, they trained one model for these many GPUs for several days, and they actually got the accurate weights for these models. Okay, so what actually we are doing on this training? We have a model, we have a bunch of internet text, which is huge. What do we do with this? The basic task of this training of these large language models is next word prediction or next token prediction. So let's say what we give the model, we actually give model a sentence, a piece of text. I grabbed the remote and switched on the, what do you think would be the next word? TV, right? So that is how it's intuitive to you, right? If I basically masked all the text and I only showed you on the, would you have predicted the TV? No, right? Because it is taking context from the earlier text. So the training model is being taught based on whatever context is there in the previous sentence. You will be able to predict the next token. And if a model, let's say, predicts something wrong, then the weights are updated so that it predicts it right. And that is how it is shown various text of the internet, and then it learns continuously, iteratively, it is able to predict the next text. And that's what it is done again and again and again for several days on these GPUs. Okay, so this is an intuitive thing, right? Anybody would be able to do that. Why do you need a large language model to do that? One of the very important thing these language models is, one, they understand the language. They would be able to see, oh, when the sentence is I grabbed the remote and switched on the, then it understands what this means, right? And then it comes up with TV. Second big task the model does is it actually gets a lot of knowledge. When you are training it on a Wikipedia page, it gets the knowledge of the world. So for example, this is a William Wordsworth poem which I actually learned in my childhood. It is called Child as a Father of, do you know what is the completion here? Did anybody is aware of this? Is anybody aware of this poem? Okay, so this is the poem, and the completion is Child is the father of a man, right? This is a very famous poem. And in this text is being fed to this model, and then model is asked to predict that man. So what model is doing, it's not only predicting based on its context, but it is also learning things. So it actually, in predicting this man, it learned the poem of William Wordsworth. So model knows the entire works of Shakespeare, Model knows entire American history, world history, geography, because it has been trained on all of these subjects. Model understands the mathematics, etc. Yes?
If it's trained on the internet, I guess, how does it know what's right?
That's a very good question. Most of the time it knows, but a lot of times it doesn't, which is called hallucinations. And that's what I will cover at the end of the lecture, where I talk about limitations of these models. So model doesn't know it is right or wrong. It is actually just auto-completing. It doesn't have a mind of its own. Model is mostly right because on internet, the text or the history or the math which is there on the internet or in the books, that is typically right. So if you can think about a model, it's basically a compression of the internet. It's basically learning the internet, but not really very accurately or identically. It is probabilistic model, yes.
What happens when there's like two opposing views? So like maybe this one is the child's father of man, the other one's the child's father of the grandfather or something like that.
Yeah.
How would it weigh which one to choose?
Yeah, so basically that's a very good question. So model is a probabilistic model. It is seeing a lot of occurrences of this text, right? This poem would be on some web page, will be in some books, some in some children's books, some in curriculum books. So the more the model encounters this man compared to grandfather, it will assign the weight to man more. So one thing which basically I didn't explain here was, when a model predicts the next token, it predicts multiple tokens with probabilities assigned to it. So the man would have the probability like 98%, the grandfather will have 0.02%. So it will predict multiple tokens, and then when you see the output of an LLM, you see the words which have the largest probability. So based on the occurrences of the words it has seen, it will actually predict the token accordingly. Alright, so going even deeper into the training aspect of it. So we have a text. How does the model actually takes the input of the word? The model takes the input, it doesn't take the words per se, it takes tokens. And there is a process called tokenization. And tokenization is done, it has multiple advantages. It reduces dimensionality. You could argue that, we have a text, what if we just feed one letter at a time, I, N, space, R, E, A, right? Model is taking, so what model does is it converts these tokens in numbers and takes the input. If we have these letter level tokenization, then you could imagine in this text you'll have a large input which is going to the model. That's why the model actually clusters this text in bunch of words. And it also, so here this is a tokenizer of GPT-4 and of this poem I told you. And you can see that these different words are different tokens. So in is one token, reactors is one token, and you can imagine the space is also part of this token. So the space, the punctuation mark, the emojis, these all things are combined when you are tokenizing these inputs. And word tokenization also fails when you have a code, something like code or a mathematical equation, because code doesn't really follow the wordings, right? So if you want to tokenize the code, these non-word tokens are really helpful, where you can tokenize the code also.
I have a question.
Yes.
So here I noticed that every single word is considered as a token, as a separate token. Is that always the case, or in some scenarios multiple words are combined to form a token?
Typically, not multiple words, but a word can be broken down in two tokens. For example, you see this toil, to and IL, space TO is different token and IL is a different token. So tokenizer, you can see either a word or a subset of a word.
So are there multiple types of tokenizers, or there is only one tokenizer?
Yes. So tokenizers are different algorithms. You can use different algorithms for tokenizer. One of the most popular tokenizing algorithm is byte pair encoding, which is called BPE. So so basically BPE works like, if you have a text, you cluster adjacent two tokens together, and you find out which is the most frequent pair of letters, and then you combine these pairs to make it one token. and then you repeat this process. And you repeat this process until you basically reach a boundary condition. It could be number of iterations of this algorithm, or it could be number of vocab size. If you want more vocab size of your large language model, you can do more iterations. So here the model has actually learned to use these words and cluster them in a certain way. And once you fix your tokenizer, it remains fixed in training and inference all the time. So here you see catalyst. Here the space and catalyst is one token and S is only one token. Okay, now let's go into the architecture part of it, how these architectures work, the LLM architectures. So you might have seen in last 2 years a very big hype in generative AI, right? You didn't see about generative AI or large language models before 2 years. Why is that? The field of natural language processing is very old. The tokenizers and the understanding text completion and question answers, they have been talked about for a very long time. But why sudden hype? One of the very big breakthroughs in this field can be attributed to this paper, Attention is All You Need, which came out from Google in 2017, and it basically introduced the transformer architecture. And this is one of the fundamental architecture which is used in large language models, in all of them really. And this transformer architecture is very powerful in understanding the language. And there is a basic operation of this transformer architecture which is called attention mechanism. And this attention mechanism is used in multiple tasks, but it's the heart of transformer architecture. But before we go to attention, let me actually think about how these tokens are converted to numerical inputs. And this is something called embedding. So you have a text. First you convert into tokens. So tokens is subword clusters you make. And these subword clusters have their unique representation in numbers. So basically each token can be converted to a number. Array of numbers, and that is unique one-to-one mapping. So if you have an array of number, you can convert it back to the token, and if you have a token, you can convert it back to the array of numbers. These embeddings are actually not only just random numbers, they are learned from specialized neural networks, and these capture the meaning of the word and the context of the word also. And for example, a word like cat and the dog, they will have very similar embeddings, but cat and aeroplane will have different embeddings because they are similar. They are both pet animals, so they actually contain information about the words and the tokens also. Now, what is self-attention? What is attention, which was the heart of transformer architecture? So if you have a text, attention basically establishes relationship between each word with every other word of the text. For example, I am going to the bank to deposit my paycheck. The park is located on the bank of the river. So think about the word bank here, right? If you hear about this bank, this first statement, you will never confuse this word bank with the bank of river. You will always think about the bank which transacts money, right? Here, if you hear about this bank, you will never confuse it with like bank with the ATM. It would always be a bank of the river. Why is that? It is because you have context of this bank is established with the rest of the sentence. Here, the context of this bank is established with the rest of the sentence. And that is how numerically the attention mechanism does. It basically establishes the context of each word, each token with every other token of the sentence. So going a little bit more mathematical into it, let's say if you have a text, and text would be a matrix. Text will have tokens and each token will have an embedding. So it will be a matrix. So from that text, you will calculate 3 vectors, key, query and value, 3 matrix. And these matrices are calculated, these are arrays actually. these arrays are calculated with the weights of the model. So you have a model, you have weights, you have learned some weights, and using these weights you can actually calculate three key query and value arrays. And then attention is basically you do dot product of key and queries. So dot product is, and you do dot product of every token with each other. So you can see if you have a sentence which is 10 tokens long, you do 10 dot product of 10 elements with 10 elements. So it's basically a quadratic operation. So if you have a word, or if you have a sentence of 10 sentences, you do 100 operations on that. So you do dot product of q and k, query and k. This you do the square root of dimension of k, and then you basically multiply it with the value matrix. So what it is doing is it is actually assigning the weight of each word to the relationship with each word. So for example, in the previous sentence, if you would calculate the attentions of bank, it will have a very high relationship with the paycheck, because typically bank and paycheck will come together. And how these attentions are calculated, when the model is learning on the entire text of the internet or the books, it will find that bank and paycheck actually come together very often. So it will have very high relationship of attention weights between the two. Similarly, bank and the river will be closely related. The weights of these two will be very high. Going will not have a very high relationship with paycheck, because going and paycheck don't come together. So when the model is processing these sentences, it is assigning these attention weights and giving you these outputs. And that is how you actually keep assigning, when you are training this model, you keep assigning these weights, calculating these weights, and updating these weights which you have with different words. So what is happening, what happens after we train the model? Model learns the language. So basically, when you give a sentence, model is able to make sense of it. Model learns a lot of facts because you have trained it on a lot of knowledge sources. It basically learns a lot of facts. One thing which is very interesting, which is not intuitive when you are thinking about it, yes?
When you say the model learns facts, is that like the model, like the probability of it predicting something given something is like 100% or near 100?
Not really. It's not 100%. The model, you can't be sure that model is accurate or not. And that is why there is an arms race between these companies, because they want to make their model more and more accurate in their responses. So there are benchmarks in the community. So if you train a model, let's say you have a company and you are training a model. You have trained a model, you can actually run this model on various benchmarks which are there, and you can see how much score you get. So some models get like 84% on one benchmark and 80% on one benchmark. And that is how these models are compared. So when I see the GPT-4 Turbo is the best model on the internet available now, because it has scored highest on these benchmarks. Yes?
Will you go over some of those benchmarks later on?
I can, yeah, I can. It's not in the slides yet, but I can go. Yeah. Now, third thing which is very impressive, it becomes creative. How can it become creative? Because it's a probabilistic model. It has learned the language probabilistically, it has learned the text probabilistically. But if you ask it to do something very specific, it can do that because of the probability. It doesn't have to reproduce the exact text which it learned on the internet, because it was all probabilistic. It can actually come up with new tokens and do new things. For example, the chemical engineering poem. It didn't exist anywhere on the internet, but it came up with it because it knows probabilistically what to do, right? What chemical engineering field is. Then I told it to make it rhyme. So it basically chose the word which rhymed, and that's how it came up with it. Now, we have trained it on the internet. It can predict next word. You can give it, let's say I'm sitting on the bank of it can predict the river. But how does it question answer? How can it become question answering machine, which is very powerful?
So I have a question there. Since it's a probabilistic operation, so let's say if you were to ask the same question again, write a chemical engineering poem with rhyme, will it always generate unique poems, or
No.
Will it generate the same poem?
It will generate different responses. Yeah. So what is happening, let's go a little deep into the operation. So each operation, each inference run of a LLM is given a seed, right? Seed is how you are initializing the random numbers of the model. And if you actually keep the seed same while running the model, it will actually generate the exact same poem, because it is going to perform the exact same operations everywhere, because initial weights, initial random numbers are the same. But if you give it different seed, randomize the seed, it will generate different poems every time. I can show you also this, I can demo this if we get time at the end. How does it become a question answering machine? And that comes with human help, right? These big companies like Google and OpenAI have employed like thousands of workers, so humans, to generate these data sets of question answering data sets. So this is one of the data set which is called Open Assistant Guanaco, and one of the example I have taken. So here this text is generated. So human is asking, can you create a function in JavaScript that returns a string of current date in this format? And then this assistant is writing this question answer. And hundreds of thousands of these question answer pairs are made by humans, and they encompass various fields. So in coding, in mathematics, in creativity, in history, in life advice, in getting time management advice. These different types of questions answers are actually written by humans, and then model is trained further on these question answer data sets. And if you think about it, this is actually the same task where you have a text. So how the model is trained? So basically, let's go into, let's say I'm training a model. I will give the model these two lines, ask it to predict this word. So it predicted the date, right? Then what I'll do, I'll give everything until date. I'll ask model to predict in. Then I'll give everything until in. I'll ask the model to predict the. So sequentially the model is predicting, and once the model is predicting sequentially, it is learning everything it has predicted before. And that is how the training is happening. And once you give the question answer format, it actually learns to answer questions also. One more thing is done after this question answer. Now the model has actually come to a place where it can answer question answer. How do we improve the quality of answering further? So these are the same poem which is generated from two different models. Which one do you like? One or two? One or two? Okay. Who are the winners? One or two? It's not an exam, so you can raise your hand. It's okay. You will not be graded on it. I promise. Okay. It's equal. This is ChatGPT, this is Llama 3. Right? Same question, different responses, and you can see they both do a good job. They all rhyme. They are very different. They actually attack the subject. So what is RLHF, reinforcement learning from human feedback? From different models or from the same model, different responses are generated, and humans are asked to rate it. So like multiple humans are asked to rate it. Let's say the humans have a consensus that this is better. Then this information is fed into the model, and the model is actually made to learn these preferences of human. And that is how model actually becomes even better. So this is called fine-tuning of the model. Now, let's come to the limitations of the model. Yes?
For the feedback, is it like if ChatGPT asks me and I give a response like, oh, I don't like this answer, is that going into the model live, or is it being compiled and then refined at a later date?
So right now it goes live.
Live.
And how does it go live? Because what these companies do is, let's say you ask the question, right? You asked it to make a poem about computer science. It made a poem about computer science. You say, I don't like this poem, give me another one. So what model will do is, it will take your initial question, it will take your take the answer, and then it will take your second question, put them all together, and then ask it to respond to that. So that is how it is actually taking the history of your conversation into account. It's just giving larger and larger text input to the model. So in today's model, the number of tokens which you can feed into the model is very large. For example, Llama 3 is 8,000 tokens, but GPT-4 advanced version takes 128,000 tokens at a one go. So it can take multiple conversations you have had and feed everything together in the model, and then it will give you a response. Google's Gemini can take up to 1 million tokens. So you can give like your entire textbooks of chemical engineering in one go and ask a question, right? Like somebody put all Harry Potter books into the Gemini and ask it to make a hierarchy of 4 different groups, like the Slytherin and Gryffindor, hierarchies of different wizards, and it made it. So it can understand these large texts now. So it's very advanced. Okay, hallucination.
Kyle, here is the question.
I have a quick question.
Yes.
So if you're doing like the feedback and then you tell the data like this is like just straight up wrong, will it ever remove data, or will it always just like store it and just mark it that this is incorrect?
So basically, it will definitely take that into account in answering your question at that time. But I'm sure these companies have mechanisms to take the human feedback. So if you go to ChatGPT or Google's Gemini, there is a question, thumbs up, thumbs down. So if you don't like the question, you thumbs down it. And then this is actually RLHF, which I explained.
Yeah, I'm talking about like that side of it, where it's like, as the engineer, you're like, this is just incorrect.
Yeah.
Will the AI like remove the data completely to like save space? Will they just like mark this is not correct?
So at that time it won't, but the company will use your response to update the model.
Okay.
Yeah. So it doesn't have in real time. Doesn't update the weights on real time, because you can understand there could be malicious attacks on these models also. Right? Somebody can go and say that every response it gives, you are wrong, you are wrong, you are wrong. If there is an automatic way to do that, they will be prone to a lot of malicious attacks. So there is a way of filtration of these responses, curation of these responses, and these responses are taken in a very responsible manner to update the model. Okay, let's talk about hallucinations. Model is very confident, that's for sure. You ask it any question, it will give you an answer. I asked him, tell me about the research of Professor Michael James at Chemical Engineering at University of Washington, Seattle. Do you have a Michael James? No?
We don't have Professor
Michael James. So, see, very confidently, renowned researcher and professor, his research focuses on development of novel materials and process of energy storage, conversion and utilization. Very confidently it answered, right? But there is no Michael Jones. And that's a problem, right? If you are a patient and asking a question about some disease and it very confidently said, oh, you don't have this disease, go drink Coke and have burgers. But it doesn't work that way, right? If you basically are talking to a Best Buy chatbot and it gives you wrong information about the price or the inventory or anything, it's very catastrophic for a company. Gen AI models. Now, one of the questions which I get is how can I get started in generative AI if I don't have any background? So I wrote a LinkedIn post on it, which I think a lot of people found it very helpful. My recommendation is to get started with machine learning first, understand what machine learning is, and part of what you are doing in this course also. And there is a very good course by Andrew Ng on Coursera, which you can take it for free. So start there. Then you can go on some of the advanced machine learning courses on Coursera or Udemy, etc. This is the link of the paper, Attention is All You Need, which actually kind of one of the milestones in spurring the growth of generative AI. There is a great researcher, Andre Karpathy, whose videos have inspired me a lot, have taught me a lot. And this lecture is a lot inspired by his explanation of generative AI as well. He has a YouTube channel, you can watch these videos and get a sense of how these systems work. And then there is a website called Hugging Face, where all the open source models are hosted. So you can download these models on your laptop for free. You can use Google Colab for actually using the GPU. So Google Colab gives free GPUs for you to use. and run these models in your machine yourself and play with these models. All right, thank you so much. Thank you for having me. Feel free to ask me any questions, and yeah, thank you.
Any questions?
Yes.
Do you think that it's possible for an AI to completely replace the human element of like any operation, or do you think it's sort of the fact that the risk of it hallucinating is like great enough that it can't reasonably like replace somebody?
So the answer is yes and no, because it can replace humans in some of the operations. For example, low bar operations, like if you want to ask a question from an e-commerce site, oh, where can I find this jacket? That LLM can completely replace, and it has replaced it also, right? Several companies have completely switched to LLMs, but sensitive applications like defense, security, healthcare, there is a lot of research needed to be done, and there will almost always need to be a human involved to give the accurate information. It depends on the application also. All right, thanks guys. Yes.
As like someone working in AI, would you like, is it their job to like consider like the ethics and stuff? Because I know with like images that are generated, it's like trained on other people's works, and I know that's an issue on like essentially stealing the work, the permission.
Yeah. So basically, the large organizations which are working on these AI technologies, they are working on responsible AI, ethical AI. So they are actually taking these considerations into account. There is active diplomacy going on. There are no laws which actually prevent these for now, but there is a huge focus on ethical and responsible AI, and people are thinking about it a lot. Yeah. Yes.
The previous slides, the guides, is that on your LinkedIn?
Yeah, feel free to follow me on LinkedIn, and I keep sharing these resources there, and and you can find this post there also. There are a lot of links. Yes.